Alright guys, my goal today is teach you as much about correlation as you need to know for IBSL. Alright, now this is a fairly simple concept. A lot of it you've probably already talked about, probably just not with the terminology that we're going to be using. So you got to get used to the terminology so that you know what we're talking about when a IB exam asks you a question about these things, okay? And also pay attention to specific numbers and ranges and things like that. Okay, now most of the statistics you've done up to this point has been univariate, okay? U-N-I-V-A-R-A-H, univariate. What that means is that there was a single variable, right? You were looking at specifically heights and how the heights varied, and you created a normal curve, and you found the mean and the median and the mode, right? All of those statistics are univariate. Even when we added in a frequency, a second column, that was still the frequency of the first column, which means we were still dealing with one single variable. We weren't looking at how two things affect each other. Okay, so what we're going to be talking about today is bivariate. Okay, which means now we're going to have two variables. Now with those two variables, one of the best ways to represent those is now using a scatter plot. And you see on this page in front of you that we have several scatter plots in front of us. Okay, now when we look at bivariate data, we often comment on the correlation. Okay, now correlation is just how well the data fits a specific pattern. Right? Correlation is there a relationship between the numbers? Okay? It doesn't necessarily mean that there's something being caused. It doesn't mean that X causes Y. There's a difference between correlation and causation. And we'll look at that in just a minute. But it does mean that there's a difference between the two. Okay? Now, with correlation, we're going to be specifically looking at linear correlations, okay? But you can have any type of correlation, so don't get stuck up on linear, but just be aware that that's kind of what we'll be focusing on. Now, if the data is increasing, as X increases, Y also increases, that is a positive correlation. Now, if they lie along a perfect straight line, then we say that it has a perfect positive linear correlation of R equals 1. Now, this R, that is called the Pearson product moment correlation coefficient. Okay, and I'll go ahead and write that down for you. There you go, Pearson product moment correlation coefficient. Now what that does is it tells us how well the points fit to a line. Now I'll talk about a little bit where that comes from later, but let's just kind of get a general understanding first. So if it's a perfect correlation, which means that the points actually lie on a straight line, and then it will be R equals 1. Now, if it's a perfect negative correlation, then the points will be in a straight line going down, which means as X increases, Y decreases. Okay, so when we're talking about positive, negative, we're really talking about Y. Does Y increases, X increases, or does Y decreases, X increases? So we go from left to right for the X, and then we talk about what's happening to Y. Okay, so now if it was a perfect negative linear correlation, then we would say R equals negative 1. Okay, so the positive and negative demonstrate whether it's a positive or negative. Okay, so this one right here, if we look at this data, you see how it's fairly obvious that the points are going up, but it's no longer a perfect straight line. But they are all pretty close. So this would be a positive linear correlation, and we would say that the R, the Pearson product moment correlation coefficient, is 0.7. Okay, now this is it's not really a strong relationship. It's kind of a moderate relationship, a moderate fit. And I'll put up a couple of ranges later, but let's just go ahead and let's look at this one, see how it's spread out a little bit more. There's still a general upward trend, right? You can see the data above and below. There's still a general trend. So it's a weak trend, but the correlation coefficient would be 0.3. Okay, now looking at these, you can see this one right here is now generally a negative. Okay, we don't know exactly what it is, but I'd guess that the R is probably a little bit better than 0.7. It looks like it's a little bit closer than those points were, so maybe an R point 0.8, 0.9, right, for this data right here. We move on to this data, so that's a very strong negative correlation, so that'd be probably around R equals negative, and let's just go 0.85. Okay, and this is just kind of a generalization. You're not going to have to be able to guess these exactly. You are going to have to say whether this is a strong or weak or a moderate correlation, and this one would be a strong correlation, as you can see, strong negative correlation. Okay, now this one's probably more of a moderate. Like it's similar to this one right here. So maybe I'd say R equals 0.7. Maybe you say, oh, that's a little more spread out. There's a little more data there. You could make this R equals negative 0.65 or something, right? And it doesn't really matter. So R equals negative 0.7, and this would be a moderate negative correlation. This one, you can see how the data is getting a little more spread out. Not quite as spread out as that one. So maybe R equals negative 0.45, something around there. Okay? Now this one, you can tell right here, doesn't have any correlation at all. Right? It doesn't really matter what happens to X, and Y could still be just about anything. So on this one, we would say there's no correlation. All right, now keep in mind the ones that we're doing right now are all linear, but this could be done for any type of function. All right, now just really quick, you do have a range of correlations. Between 0 and 0.25 is very weak, so that's where it's really, really spread out, but still kind of fits something. You got 0.25 to 0.5, which would be considered a weak correlation, which would be something like this, and then 0.5 to 0.75 is moderate, where it's definite that it's following this trend, but it's not really, really tight. And then you got 0.75 to 1, which is strong. Now notice this is the absolute value, which is why it also fits for the negative correlations, which are a negative R. All right, so that hopefully gives you the basic idea, and we'll, like I say, we'll get into some of the more details of that later. Okay. Let's go on and look at correlation and causation. This is one of my favorite examples. Global average temperature versus the number of pirates. This is real data. Okay, you'll notice that each of the points is labeled with a year, and the fact that the years are different doesn't really matter, because I'm not doing anything with the years. I'm actually doing the number of pirates and the global average temperature. Right? So I go number of pirates, and it looks like as the number of pirates decreases, the global average temperature increases. And so a very inexperienced student may say, well, that means that as we kill off pirates, the global average temperature is increasing. So therefore, us stopping pirates is causing global warming. Now, of course, that doesn't really make sense. Yes, that's what the data shows. The numbers show a positive correlation. That's probably a strong positive correlation. Right? But the fact of the matter is that the number of pirates doesn't affect global temperature. So what we say is there's some type of confounding factor. Confounding. Okay, now that confounding factor could be one thing, it could be several things. In this case, it could be technology, right? As technology gets better, it gets easier for us to stop the pirates, right? As our ships get better, it's easier for us to find them, it's easier for us to capture them, it's easier for us to stop them, so the number of pirates decreases. Technology, of course, also increases the amount of greenhouse gases in use, and therefore the global average temperature will increase. And so, you know, you could have some other factor that's affecting this, that's not causing it. There's a correlation, yes, but that doesn't necessarily mean that it's causing what's happening. Okay, another great example would be shoe size versus vocabulary, right? If you just go out to the mall and measure shoe sizes of people and then give them a quick vocabulary test, I think you would find that as the shoe size gets bigger, the vocabulary would also get bigger, right? Well, that doesn't have anything to do with the shoe size. It has to do with the fact that a person with the smallest shoe size is probably younger, so therefore has a lower vocabulary. And so again, there's a confounding factor, which is age, which affects the relationship. There would be some type of linear fit, linear correlation, positive linear correlation, but it would not be a reason for cause. And so be aware of that correlation and causation don't necessarily mean the same thing. All right, what we want to do now is our final little bit, which is going into the line of best fit. Okay, so as we're doing the line of best fit, what we're going to do is add in one piece. You've probably done this before where you just said, okay, let's eyeball a line of best fit. We'll put the best line of best fit in, write an equation, etc. Okay, what I want to do today is introduce you to one new idea, which is called the mean point. And if you've used the mean point before, great. And if you haven't, well, then I'm going to introduce it to you now. Now what the mean point is just the mean x value, comma, the mean y value. And that gives you the center point on your graph. You can tell that this is a linear correlation, probably a strong positive, right? This is probably a 0.9, maybe 0.85, okay, but definitely a strong positive correlation. So we're going to go ahead and try to write a line that fits this data. In order to do that, we're going to find this mean point. Now to do that, we're actually going to find the average of the x values, which is the total fat, and we're going to find the total fart, oops, and we're going to find the average of the y values. Now you could do this by hand. I'm going to show you how to do it on the calculator real quick. So we're going to open up our calculator, and the way to do this is we're going to put it into the list. You've done this before, so we're going to go we're just going to go into stat, and then we're going to edit, so we can go straight into our list, and you'll see that I actually already have my data here. So you put the x values in list 1 and the y values in list 2. As you can see, I've already got all the values there. Now, if all I need is the averages of those, then what I'm going to do is I'm going to do what I have done before. I'm going to go into stat, and we're going to calculate, and this time we're going to do two variable statistics. The one variable statistics takes the first column as your data and the second column as your frequency. For the two variable statistics, we're just going to do this and push enter. It'll take you to the home screen, push enter again, and now there's your x average, which is 22.45. So 22.45, comma, and then you'll notice that that gives you the sum of the x values, sum of x squared, gives you the standard deviation, all that kind of good stuff. And then we go down to the y, so the average y value is 457, just like that. Okay, and I'm just going to write down 3 sig figs there. So 457, all right, so we've got our point there. Now this point we can go ahead and put on the graph. So we go 22.45, so about 22.5, which would be right in the middle there, and then 457. Okay, so that's that point right there. Oops. There we go. So somewhere right in the middle there. Okay, now I'm going to draw my line of best fit. And so we're going to draw a line. Now when we draw our line, we're going to try to fit the data as best as we can. You can change the slope as needed, but your line of best fit should go through your mean point. Alright, so I'm going to see if I can get it where I want it. And well, it looks like that's about as best I can do with the program I'm using. So it's going through my mean point there. Alright, so now my line of best fit more or less fits my data. The idea is that you have just as many points going above as below. And you may say, well, let's kind of adjust this just a little bit. Maybe it needs to be a little bit higher because of that right there, which means that this one will lower a little bit, and that looks maybe like it's a little bit better. There we go. Alright, so now you can see I got about the same number of points above and below. At the top I got points above and below, and at the bottom I got points above and below, and so it's fitting the data fairly well. Okay, so from this point I now want to be able to write an equation. Now to do that, I'm going to need the slope, and then I need a point. And so I'm going to be using point slope, so y minus y1 equals m times x minus x1. Alright, and with that I can then have a linear equation. So I need to find the slope, so I'm going to use 2 points. Now one of the points I'm going to use is going to be the mean point. So y2, so that'll be 457 minus y1. Now I'm going to take another point here. I'm going to take this one because it looks like it's going right through that point. So it's not quite the biggest one. It looks like it's the next biggest one. So that looks like it's probably the big burger right here, because there's 2 at 31 there, and it's the bigger of the two. So it's 560 and then 31, and then the x value would be 22.45. When you're writing your final answers, you want to write it in 3 sig figs. However, throughout the rest of the problem, you want to keep as many digits as possible because that'll help make your answer a little bit better as far as accurate. So from here, we're going to go ahead and get our slope. So we're going to go 457 minus 560, and then divided by 22.45 minus 31. All right, and we go enter, and we get a slope of 12.0 because that's all going to round down. So 12.0, and I do want 3 sig figs, so I'm going to put the 0.0. So I'm going to go y minus y1, which is 457. Again, I'm going to use the mean point here because that one I know is right in the center of my data. And then 12.0 times x minus 22.45. Now if I take the time to rearrange that, then I will get this, 12.0x plus 188, which looks like it could be just about right with my y-intercept. And this is, by the way, rounded to 3 sig figures, but there is my linear equation. Now, I want to actually take the time to show you how to do this on the calculator as well. All right? So, calculator again. I've got all the data in, which is great. Let me just show you this first. We're going to go to second y equals, which will give me the stat plot. Now, if I go to number 1 and turn plot 1 on, so it goes from L1 to L2. Okay, if I push enter, it'll bring up the list, and we're doing a scatter plot, which is this option right here. The x values are list 1, the y values are list 2, and this is just going to give us a big round point. If you want smaller points, you can, or you can use a plus sign as well, where the center of the plus is the center of your point. I like the big ones, it's just a little bit clear. Now, I'm actually going to have to go to the window as well, because I need to change the window to fit the data that I have here. So my minimum x is going to be 0, and my maximum x, it looks like, was 34, so I'm going to go up to about 35. Okay, and you don't really have to change the x scale, but I'm going to go by 5s. The y minimum, again, we'll go ahead and just say 0, and the y maximum goes up to 590, so let's go up to 600. Again, you don't have to change the y scale, but I'm going to go ahead and put about 50. And you'll notice that when I graph it now, I actually get the graph of my scatter plot. And this step is not necessary. It's just if you want to have a way of visualizing it to double check your work by hand or something like that. Okay? Or if you had to do it by hand, this is now a way to double check to make sure that you actually did it correct, because the calculator is going to do it all for you. Alright, so now what we're going to do is we're going to go and calculate what the line will be. The calculator will actually do this for you. What we do is we go into stat again, and then we go calculate. Now inside the statistics, we're going to choose lin reg. Now notice there's also quadratic regression, a cubic regression, a quartic regression. Again, we'll talk about regression in the next video. I just want to, the next segment, the last little part of this, but we're going to do the linear regression. And you push enter and push enter again. Now this is automatically going to use L1 and L2 for your data. Okay, so when we push enter, it'll do the calculations, and notice it came up with a slope of 11.7 and a y-intercept of 193, which is pretty close to what we got, right? Now if you want to put this into your graph, you're going to have to write down the numbers. You should be able to do some type of store or something if you wanted, but y equals 11.7x plus 193.8, so 194, and then you can put that straight into your calculator. Now the nice thing is, with one of these equations, you can now make some predictions. You can say, okay, what if whatever restaurant this is came out with the super burger, which had, you know, twice as many patties or something like that, and it had a total amount of fat of, you know, 50 grams. You could then calculate approximately the number of calories that that burger would have. Okay, now I just want to close by talking about a little bit of the theory. Okay? All right, so Now, I've told you guys before, the calculator isn't really smart. It can't really calculate these things. What it's doing is it's really fast is what a calculator is. And so it's actually doing a whole bunch of guesses. Now, I'm going to talk about just kind of the theory, the idea behind it. Now, there is a way to actually calculate the correlation coefficient by hand. There's a way to do this regression by hand, but it would just take you forever because you have to keep changing things. Now, the correlation coefficient, there is a formula, but it's complex enough that they don't require you to know it in this class. One thing I did forget to mention is that when you do your two variable statistics, beep, and you push enter, it actually, as we scroll down, after the y values, well, it didn't give you the correlation. That's right. The correlation coefficient will come when you do your best fit. But if you want the correlation coefficient from your best fit line, from the regression, then you actually have to go into the catalog. Okay, so go with me into the catalog. The catalog is right down here. So it's second 0. Okay, now in the catalog we have to go down to diagnostics. Now this is usually off, I think just because it slows down the calculator a little bit. So I just went down to D, and then I'm going to arrow down until I get to diagnostic. Okay, there it is, diagnostic. So I'm going to turn the diagnostic on. Now what that does is you have to push enter. Now it'll say done. Keep pushing enter until it says done. Now when I go into the stats and do the the linear regression, then it'll give me the same numbers as before, but this time it will actually give me the R, the Pearson product moment correlation coefficient. So note that it was a very strong correlation. The points were very much in a straight line. Not quite perfect, but they were pretty good. So there you go. There's how to get R on your calculator. Now what this is doing when it does this regression is it says, okay, let's consider a line. Let's just draw a line, make a guess is what the calculator does. Then it calculates what's called the residual. The residual is how far each point is vertically from the line. Okay? Now, part of the problem with that is you have positives and negatives, and it wants to get all those points as close to the line as possible. So positive and negatives are going to play havoc because then you've got ups and downs, and the positive and negatives are going to cancel out. And if these two right here cancel out, then it's going to say that it's perfect. It's 0, which is the best it can do. So what it's going to do is it's actually going to take this and it's going to square it. Okay, so it takes the residual, how far it is from the line vertically, and it squares that value, and then it adds them all together. So that would be the sum of the r squareds. Alright, now you could do this by hand and you could find out what the sum of the r squareds is, but then what the calculator does, it says, okay, well what happens if I change it just a little bit? What happens if I take my line and I move it down just a little bit like this, and I move this side up? Now it has to go through that mean point. And so it can't just shift the whole line down, but it can kind of twist it at an angle, right? It can kind of change it so that it looks like this instead. And so it can keep playing with that line. And what it does is it just keeps guessing over and over and over again, like 1,000 times, maybe 2. I have no idea how many times it does it, but it just keeps guessing and guessing, and it keeps checking the sum of the r squared values. And if the sum of the r squared values is smaller than it was before, then it's telling you that the points are getting closer to the line. If the sum of the r squared values is getting bigger, that means your residuals are getting bigger, and so the points are getting farther from the line, and so it'll go back. And so it just keeps playing with that line until finally it gets to a point where it says, okay, this is as close as I can get, I'm done guessing, and that's the end. And so, for example, here it would just take p squared, which is that residual, plus q squared, plus r squared. It would add all those numbers up together, and it would get the overall residual, and it would try to find which line would give you the best sum of the residuals, or where the sum is the smallest. Okay, that's also why on your calculator, when you looked, there was an r squared, because that's the sum of all of those residuals, the sum of all those distances. That is going to be less important than actually r here. Okay, so that's the basic idea behind what we've got. And actually, sorry, that is not the sum of the residuals. It's part of that formula, but then you have to square root it to get the R value, which then can be anything between -1 and 1. So basically that's all we've got on correlation coefficient, and I hope that helps you as you kind of, this is your last topic for IBSL. All right, so good luck on the rest of your journey.